Now, in this package, we are going to look at application of partial derivatives. We are going to look at application of partial derivative by Jacobian, that is using Jacobian to solve implicit differentiation. We are going to also look at application to Taylor series. Now, we'll also look at application to maximum and minimum. We are also looking at application by Lagrange multiplier. We will look at application of derivative, that is to directional derivative. We look at application to normal and other applications that we'll look at. So in this package, I urge you to sit down and bring your book and pay adequate attention, because there are lots to learn in this package. Now, the first application we look at is application to partial derivative of implicit function using Jacobian approach. Okay. Now, if f of x, y, uv equals 0, that is f1 of this, and we have f2 of x, y, u, v equals 0, defines u and v as implicit functions of x and y. Then partial u partial x will be equal the Jacobian of f1 f2 over x and v over the Jacobian of f1 f2 u and v. Now see, by Jacobian method we can find partial u partial x of implicit function. Now see, when in this package, if you can recall, when we were dealing with implicit function, we use determinant approach to get implicit function, where we define the function and then we use Cramer's rule to get it. That is another way. We can also apply this using Jacobian. If I have two equations of this form that defines u and v as function of x, y implicitly, then partial u partial x, find it partial u partial x, is the same of f1 f2 with respect to x and v divided by the Jacobian of f1 f2 with respect to u and v. So we are going to look at an example so that we see how it works practically. Now we'll look at this example. If u squared plus x v squared minus xy is equals 0, and u squared plus xy v plus v squared is equals 0, define u and v as implicit function of x and y, we're going to find partial u partial x. Now remember that this one we are using Jacobian approach. So we have other approaches which we have already dealt with still in this package. The solution. Now u squared plus x v squared minus xy equals 0. Let's f1 equal u squared plus x v squared minus xy equals 0. Then f2 will be equal u squared plus xy v plus xy v plus v squared. Yes. Okay, so we have these two now. Now, we have said that partial u partial x will be equal the Jacobian of f1 f2 with respect to xv divided by the Jacobian of f1 f2 with respect to uv. So let's take the Jacobian of the up first, which is f1 f2 with respect to xv. Now we know that partial f1 partial x will be equal to v squared minus y. See, partial f1 partial x is v squared minus y. So partial f1 partial v, because we are doing with respect to x and v, will be equal to 2xv. 2xv. Right. Now partial f2 partial x, partial f2 partial x will give us yv. We'll also look at partial f2 partial v. It will be equal xy plus 2v with respect to v. It was xy plus 2v, which means the Jacobian of f1 f2 with respect to xv will be equal to the second order determinant of v squared minus y 2xv. Then we have yv, and then we have xy plus 2v. So now we'll take determinants, and this here times this will have v squared xy, that is this times this, plus v plus 2 v cubed, no, this time this was 2v cubed, minus x y squared, then this time this will give us minus 2 yv. If we go this way, we'll have minus 2 xy v squared. So that is what we will have. We use this to find this minus multiplication of this, which is the same as, so okay, so this will be the same that Jacobian of this, that is the Jacobian of f1 f2 with respect to x and v. Okay, so the next thing we'll do is, now this one is 2, look at minus 2xy v squared, and I have xy v squared, so minus 2xy v squared. I can write that as 2v cubed minus xy squared minus x minus 2 yv minus xy v squared. You know, this one is minus 2xy v squared, so this is xy v squared. So they remain this. That is the Jacobian of f1 f2 with respect to x and v. Now we can also look for the Jacobian of f1 f2 with respect to u and v. And so what we need here is partial f1 partial u. Partial f1 partial u from here will give us 2u. Yes, 2u. Now partial f1 partial v, partial f1 partial v will give us 2xv. Now partial f2 partial u, partial f2 partial u, it's also giving us 2u. Now partial f2 partial v, and partial v is giving us xy plus 2v. so that the Jacobian of f1 f2 over uv will now become, is the second order determinant of the first derivative of f1 with respect to u and v, and f2 with respect to u and v. So which we have 2u 2xv 2u xy plus 2v, and if you do that, we'll have this will give us 2xy plus 4uv. That is this way, and going this way, have minus 4uxv. Yes, minus 4uxv. Okay. Now, partial u partial x then becomes the Jacobian of f1 f2 over x and v divided by the Jacobian of f1 f2 with respect to u and v, which means partial u partial x will be equal to v minus x y squared minus 2y v minus x y v squared divided by this Jacobian, which is 2x y plus 4uv minus 4ux v. So that is partial u partial x using the Jacobian approach to differentiate implicit function. Now we'll look at another application of a partial derivative. Now another application we want to look at is Taylor's series for function of two variables. That is Taylor series expansion. Taylor series expansion for functions of two variables. Now let f of xy be function of two variables x and y, whose finite partial derivative exists and continuous in the interval a less than equal x and less than a plus h, and b less than equal y and less than b plus k. Then f of x plus h y plus k will be equal f of xy plus k plus 1/2 factorial h plus k plus 1/2 factorial times h partial x plus k partial y f. Let me expand this so that you really understand what we are saying. That if a partial f partial y plus 1 over 2 factorial. Of course, if I expand this place, you know this is square. So I'll have a square partial square f over partial f squared plus hk. Then 2 partial square f partial x partial y plus what we have k squared. Then we'll have partial square f over partial y squared plus, yes, that would be the expansion of it. Now, to simplify it more, we can write it in this way. That this will be h. You know, this is h partial f partial x plus k partial f partial y plus 1 over 2 factorial. Then I will have h squared partial x, right? That is second partial of x plus hk2 partial s, the cross plus k squared. Then I have of sy. Okay, notice that this factorial, these two factorial multiply all this. Now we are saying that f of x plus h and then y plus k will be equal this. Now let's see the proof. Now consider the plane below. We'll use this plane to prove the Taylor series of a function of two variables. We have a point in this place. This point is p x y, and now in this point, if this point from here to here, you know, this is the x-axis and this is the y-axis, then at this point R, there is increase in x. So I have x plus h, y is a constant at that place. Now if we move to this point, call this point Q, x plus h is a constant here. You know, we have already had it here. So moving to this place, there is increase also in y, and the increase is k. So that's what we have. Now we noticed that for points R, if we deal with these points, f of x plus h, y, this point will be equal to f of x, y plus h plus h. We have f of x, y plus h squared over 2 factorial. Then we have f of x, that is second derivative of x. You know this using the pattern of Taylor series of one variable. You know, everything we are doing here is calculus of several variables. You know, it is believed that the student know elementary calculus very well. So if we use that pattern, now this is 1, call this 1, equation 1. Then if we move to point Q, at point Q we have f of x plus h and y plus k. You see that? That is for this point. It will be the same as f of x plus h y. That's what it will be. Plus. Then we have h, no, plus k. You know, there is increase here, k. Because y increases. Yes, okay. So if I have k, I have f of y. Then I have, this is x plus h. y. Another increase again here become plus k squared all over 2 factorial, and then we also have f of what? X. That is y, the second derivative of f, y, plus. Okay, but don't forget there is f, that is x plus h and y there. So if we have that, we can call these 2. Then as in this place, I'm going to differentiate 1. Differentiating 1 with respect to y. I want to differentiate 1 with respect to y in this equation now. So I will have partial f partial y x plus h y will be equal f partial y xy plus h partial x partial y, that is the cross partial of xy plus h squared over 2 factorial. Then I have partial x partial y of x y. So another one again, I'm going to differentiate. I'm going to differentiate this. So let me call this 3. I'm going to differentiate this 3 with respect to y again. And that will give me f partial y. That is the second partial of x plus h y, and then this will give me the second derivative again of xy is equal to plus h. Then I have x y and y again because I'm differentiating here again with respect to I have x plus h squared over 2 factorial. Then I have x y y. Okay, then I have x y. This is 4. I have 4, equation 4. Now going back to 2, let's come back to 2 because we want to define 2. We want to see whether 2 can give us this that we express. If we go back to 2, we now see that we have f of x plus h y plus k will be equal, see what this one said, see what this one. And this one said f of x plus h and y is constant. So which function is this? Is it not this function of 1? That is what 1 expressed. So we will now put 1 there, which gives us f of xy plus h. Then we have f of xy plus h squared over 2 factorial. Then we have x, of course, this is of xy. Then, that is the first one we have expressed. Plus k. So, plus, I'm trying to do that so that this thing will reach. Plus k. Let me do like this. Plus k. See k here. K. And then we look at partial f partial y. Which function is this particular function? Look at the function here. This function. So we put that. Now give us partial f partial y of x y plus h. Then we have f of xy, that is the cross partial of x and y, plus h squared over 2 factorial. Then we have xy of xy plus, okay, now we are finished with that, plus k squared, so I have to take that, plus k squared, that is k squared over 2 factorial. Then we look at this function, the second derivative of f with respect to y. Now this function is, look at this, is this. So we put that, and that is f partial f, the second derivative of f with respect to y, xy plus h x y xy f of xy plus h squared over factorial. Then we have f x y x of xy plus, okay, so now look at that. Now what we do now is we are going to collect corresponding order. Now see this one, and when you do that, you take this order. Now what we do now to cut it short, we are going to, it's always multiply k through, and we also multiply k squared over 2 factorial through. And when you do that, you collect the like orders. As first partial, second partial, them together. You have that f of x plus h and y plus k will be equal f of x y, which is this first one, plus then you have h partial x. If I'm changing this sign now, I want to, this sign means partial f partial x, which is this. So I try to put it there. Partial y plus 1 all over 2. Then we'll have h partial x plus k partial y f. This continues. So we have f of x y plus, this will give us h partial f. I'm using this f, okay? I'm using f to times it over partial x plus k partial f partial y plus, okay, the expansion of this 1 all over 2 factorial. Now here is 2 factorial. Then h squared partial square f over x squared plus hk plus 2xk. Yeah, by binomial expansion. That's what we did. By binomial expansion, you have this. Then f partial square f partial x partial y plus k squared, and then we have partial square f partial y squared. Now see what I have here. Let me put this so that this 1 over 2 factorial, multiply all of them. Okay, let me change this partial again to the original state that we have. We will have x plus h y plus k will be equal f of x y plus, see this, plus h f of x, partial f partial x plus k. We have partial f partial y, okay, plus 1 all over 2 factorial. Then we will have what? H. Now look at this, partial x plus 2 hk. Then we have partial x y plus the last one here, which is k squared. Then we have partial y. Now if you compare this with what it states here, you see, you are able to show that for any function of 2 variables, say x and y, that if you expand the function, the increase in x and y will give you this. You see, this thing continues to third order, fourth order, infinity. So it is assumed that the students are familiar with series expansion. If you are not too familiar with it, you get our on series expansion, you know a lot about finite and infinite series. Yes. So let's look at an example of this and see how we apply it. So the example we are going to take now is this. Expand z is equal exponential 2x cos 3y in the power of x and y up to the quadratic term using Taylor series expansion. Okay, let's pick the solution. We know that for any f of x plus h and y plus k, that we will have f of x y, see that f of x y plus h partial f partial x of x y plus k y of x y plus h squared over, or if you don't have, we do this factorial. This is what we did, and will give us h squared partial, the second partial of f plus 2hk. Then we have f of x y plus k squared. Then we have of x y. You know that. Okay. Now note that in this expansion, that if h become k, that is, if h is equal x and then k equal y, we also have that x is equal a and then y is b. Then we will have that f of h is now x. So you have x plus a, because a here, x is a. Okay. So h is x, so we have a plus x. This is something as x plus a. And then we have y plus b will be equal f of ab. You know, this thing is taking a and b now. F of xb plus x. And then we have x of y plus k. K is now y. So you have partial f partial y of, okay, look at here is a, sorry, a, b. You know, we have changed x and y to b. Then we'll have this. Then we have ab plus 1 over 2 factorial. We have x squared partial, the second partial derivative of f with respect to x. Okay, now we have ab plus 2xy. And then we have f of ab plus y squared. Then what do we have here? Here will be f y y. Then we have ab. Okay, so that is, this ab is the point that we are expanding about. That is the point we are expanding about. So in this question, we are expanding about the power of x, which is about x is equal 0. That is what it means. In the next example, we can look at other ones that will expand apart from 0, other points, so that we really understand what we are talking. Now, here, if I have this, in this function, you know, what we have here is f of xy. Yeah, is equal, now let's say it's equal f of xy, so that we have f of xy equal exponential 2x cos what? 3y. Now what we need is all these points, this is what we are going to expand. To do that, we'll start with the first. We are expanding about x is equal 0, y equals 0. So we'll start that here. Now f of 0, y 0, which is this place, will give us what? Exponential 2 times 0 cos 3 times 0. And that will give us what? And this will give us, anything less than 0 is 1. So we have 1. Now cos 3 times 0 is 1. So at that point, what we have is 1. And the next one is here. Partial derivative of f with respect to x at the point 0, 0. First, let's find f of x here. The partial f partial x. And that will give us f partial x of xy. We want to differentiate here. So we are differentiating with respect to x. So what I will do, 2x squared 0 plus cos 3y, we differentiate this and it will give us 2 exponential 2x, which is equal to exponential 2x cos what? 3y. Now if we put 0 and 0, which we are differentiating about, that this will be the same as 2 exponential 2 times 0 cos 3 times 0. Now this will be the same thing as 2 for here, because anything less than 0 is 1. So 1 times 2 is 2. But this one is cos 0, which is 1. So we have 1 at this point. So that is f partial x of AB, and then AB is 0, 0. At this point will be that. Now another one we are going to differentiate is this, which is partial f partial y. Now see the function here. Partial f partial y xy will be equal, now look at that. If you differentiate this, that is exponential 2x, keep exponential 2x, differentiate here, you have minus 3 sine 3y plus, keep cos 3y, differentiate this with respect to y is 0. So if you do that, what we have is minus 3 exponential 2x sine 3y. Now at the point 0, at the point where x and y is 0, we'll have that this is the same as minus 3 2 times 0 sine 3 times 0. Okay, so everything becomes 0. At that point, it is 0. Alright. Now, the next point we'll look at is which point? Okay, this one. This one. That means f partial x, that is the second derivative of f with respect to x, the second derivative. So we will now go to here. This is the first derivative, right? And the first derivative, see what we had. This one. So we are going to differentiate this place the second time, because this is the first. So we differentiate the second. The second derivative, what we do here is you keep 2 exponential, 2x, keep it, differentiate cos 3y, we have 0, plus keep cos 3y, differentiate this with respect to x, I will have 4 exponential 2x. Now that means that at the point 0, at the point where x is 0, y is 0, this one is 4 exponential 2 times 0 cos 3 times 0. Now, what will this give us? It will give us 4. 4 times 1, which is equal 4. Now, the next one, yes, from here, we have reached here. So the next one is here. And what is this one talking about? 2xy. 2xy. X, okay, you have something here. X, this is xy. xy, and this is also xy. See? xy. That is the cross partial. Someone talks about the cross partial. xy. Now, that one, xy, and that is it. The partial derivative of the cross partial means that the partial derivative of f with respect to x. So this time, I'm going to differentiate it with respect to y. That is the cross partial. Okay. Now, and that will give me 2 exponential 2x times, to differentiate cos y, cos 3y, you have minus 3 sine 3y, right, plus cos 3y, then times 0, because this one no y, and that will give us minus 6. Yes, it will give us minus 6 because this one is 0. Minus 6 exponential 2 times 0, and then I have sine 3 times 0. Everything is 0 in that one. And then another one will go as the last is here. As it is here. And this one is the second derivative of f with respect to y. And so what we'll do is to go to y and differentiate it again with respect to y. So what we'll do that is f partial f, and the second derivative of f with respect to y will give us minus 3 exponential 2x, that is keep this one, then differentiate this with respect to y, we will have cos 3y plus, if you keep this, sine 3y, I give sine 3y, then differentiate this with respect to y. You see, I keep the first one, I differentiate this, okay, here will give me 3. I keep 3, so I will have this 3. This is 3. Cos 3y. Yeah, that is what it means. Then I keep sine 3y. Differentiate the other side is 0. So what I have here is minus 9 exponential 2x cos 3y. At this point, if you put 0 here for x and put 0 for y, of course we will have minus 9 times 1, which is minus 9. Now look at that. So now we want to do the expansion now, and what we'll do is we now see that f of xy, f of x, yes, f of x, y will be equal. You know why we say f of xy? It will have been f of x plus 0. You know, x plus 0 is still x, and y plus 0 is still y. So f of xy now that we are expanding, which is equal to exponential 2x cos 3y. Okay, let me put that straight. Now, expansion of exponential 2x cos 3y, so you understand, is the same as f of, now start here, f of AB. Now f of AB was this, basically was 1. Right, so we first have 1 plus, we come here, you have x. Now, partial x at the point AB, which is in this context 0 and 0 for x and y. Now see that. Give us 2. Okay, so we should not forget this x, which I have written. So we have 2 at that point, plus y, and then partial f partial y at this point give us what? 0, plus we have 1 all over 2 factorial. Yes, we have x squared. The second derivative of x of f with respect to x, which is this, at that point give us 4. Alright. Then the next one is this 2x plus 2xy at this point 2xy, that is a cross partial, was 0 plus y squared, and then we have the second derivative of f with respect to y, which is minus 9 okay, minus 9, and that means this will give us 1 plus 2x. Of course this will go. If you time this, you have plus 2x squared plus 2 factorial is 2. So by timing with this, of course if you time this, it becomes 0. And if you time this with this, you have minus 9 over 2, minus 9 over 2 y squared. That is, I'm using this to open this bracket. Okay, okay. I will not continue because they say we should expand it to the second degree. So that is what we have. The expansion of f of xy equal exponential to x cos 3y is the same as 1 plus 2x plus 2x squared minus 9 over 2y squared. So by Taylor series, we are able to expand this function about x is equal 0 and y is equal 0. So, and give us the series. This is how it works. Okay. So the next example we are going to take is this. Now expand x squared y plus 3y minus 2 in powers of x minus 1 and y plus 2 using Taylor's theorem up to the third order term. Right. So let's take the solution. This one is third order term. Now we know that f of x plus h and y plus k will be equal f of xy, right? Plus, now let's do make it the way that the understanding will be more. Now you can write it in this way. Plus we have 1 over 2 factorial. Then we have h partial. Don't forget there is f here. So partial x plus k partial y f squared plus 1 over 3 factorial. This is the one that will give us the third order. So we have h partial x plus k partial y f k. The thing continues, but we are asked to stop at 3. That is the third order. Now, if we have this, we can write it in this form: plus h partial f partial x plus k partial f partial y plus 1 over 2 factorial. Then by binomial expansion, we can expand this to have h squared partial square f over partial x plus hk. 2hk here. 2hk, by binomial, you say h squared 2hk. Then we have partial square f partial x partial y plus k squared partial square f over partial y squared. That is the expansion of this place. Then after that, we will also expand here to have plus 1 over 3 factorial. Then how do we expand here? By binomial expansion to, we can have h cubed partial cube f partial x cube plus 3a square partial square f partial x square. And note here we will have k, then we have partial f partial y. If you know binomial expansion it's in first course mathematics, we did binomial expansion. You know that what we are doing here, we are taking from binomial expansion, and so if you do that, the next one that you have is 3. Then h reduce, you know, h is reducing, y k will be increasing, and so in that aspect we have that h will have then we have partial f partial x, then k will also increase. And then we have partial square f partial y square, that's it. Then plus k cube. And then when you have k cube, you have partial cube f partial y cube. So that is the function by binomial theorem. Okay. Now this thing that you see here is what we are going to do. We are going to expand so that we use it for this function. Now, and we also know that this is the same as f of xy plus h partial f partial x. So I want to simplify it. Plus k. Then we have partial f partial y plus 1/2 factorial. Then we have h squared. Then we have the second derivative of f with respect to x plus 2 h squared. Then we have what? F of xy plus k squared. Then we have the second derivative of f with respect to y plus 1/3 factorial. We have h cubed. Then we have f(x) that is called derivative of f with respect to x plus 3a squared k. Then what we have here is f(x) y, and then we have again plus what next? 3. We have h k squared, and then we have f(x) y is double, x is 1, so plus k cube. We have the third derivative of f with respect to y. Okay. Now that is what we will find. All these ones we will find them. Now see the function here. F of xy is equal x squared y plus 3y minus 2. That is the function we want to expand. And then we know that, see, the first point here is f of, but we need to find one thing. What is x? What are we expanding x about? See, we are expanding x powers of x minus 1, which is x is equal 1. The power of y plus 2, that is the same thing as y minus 2. So what we'll do now is we're putting x is equal 1, y minus 2. Alright. If we do that, see, x is equal 1, y is equal minus 2. That is what we are expanding about. So now, f of 1 and minus 2 will give us what? 1 squared minus 2 plus 3 minus 2 minus 2. Then this will give us what? This will give us minus 2. And this is what? Minus 6 minus 2. And then what we have is minus what? 10 in that place. Then the next one we'll do is the partial derivative of f with respect to x, y. With respect to x, partial derivative of f with respect to x will give us, now see, f of x. So with respect to x, we will have 2xy. We have only 2xy. Now if we put the value of x equal 1 and y minus 2, we will have 2 times 1, then minus 2. And this will give us minus 4. I've got minus 4. Then again, what we want to differentiate is which one here? Partial derivative of f with respect to y. If you differentiate this with respect to y, you have x squared plus 3. Yes. And then if you put the points x is equal 1 and y is equal minus 2, we then have 1 plus 3. So no y. So we have 4. Now the next one we differentiate is here. The partial derivative of f, the second partial derivative of f with respect to x. Now second derivative of f with respect to x is partial f x xy. And that will give us, if I differentiate this with respect to, no, I've already differentiated it, now I'm differentiating it with respect to x. So I will have 2y. Now there is no x, I'm going to put only minus 2, will give me minus 4. Alright. And the next thing, we stop at this place. So I'm going to differentiate this. The cross partial, so I'll go to here, I differentiate it with respect to y. Look at it. With respect to y. This time. Yes, with respect to y. I differentiate this one with respect to x, so I have 2y. So I want to differentiate with respect to y. I will have 2x. So we are talking about the cross partial is 2x. Now if I put the value that x is 1, I will have 2. Now also group, which one do we stop now? Here. That is the second partial derivative of f with respect to y. Now I'll come to y again. Also differentiate with respect to y. That is 0. Okay? So that gives me 0. Now the next one again is this. I will go to where I differentiated this. So I'll differentiate again with respect to x. I have to differentiate again the third time, which is this. So I now see that the third partial derivative of f with respect to x is 0. Now I go again to the second partial derivative of f with respect to x, and then I differentiate with respect to y. So that was this. If you differentiate with respect to y, you have 2. So we have this x, y is 2. So at the point x and y is 2. Then we go again to this one. Go to cross partial and differentiate it with respect to y. That is what it means. Yes, cross partial. The cross partial was here. So if I differentiate it with respect to y, x, y, y, I have 0. Okay, now the last one, we have the third partial derivative of f with respect to y. So I will go here and differentiate to y, it gives me 0. So I have y is 0. Now it becomes very simple as ABC to fix this value in this series. It becomes very simple. So what it means is that x squared y plus 3y minus 2, which is the function. Yes, which is the function, is equal to you see, f of xy. In this context, f of xy, that is at the points x is equal, at the point x is equal 1 and y is equal minus 2 was minus 10. So this one now is what we are talking about. Minus 10. So that is the first term. So I'm going to put minus 10. The first term here is minus 10 plus h. Now don't forget that h is x, yk is y. So I can try to write it this way. Now I will write it this way. X. Then I look for the first derivative of f with respect to x from the series. You see this term, this place. So what did I have from that place? Minus 4. So I will now put minus 4 plus. Next one here is k, and then k is y. Then I have partial derivative of f with respect to y. Give me 4. So I have 4 plus. Next one we have is 1 all over 2 factorial. Then I have a squared, which is x squared. Then the partial derivative of f, the second partial derivative of f with respect to x, is where we are looking at. And then that gives us what? Minus 4. That gives us minus 4. So we have minus 4. And then the next thing again we'll do is plus 2 ahk 2. That is xy. Then we have the cross partial, which gives us 2. So we have 2 plus k squared, which is y squared. We also have that place of y squared. That's now partial derivative of the second partial of f with respect to y give us 0. So we'll have 0 in that place. Plus 1 all over 3 factorial. Yes, we have ah cube, that is x cube, and then if we have x cube, we look at it, the third partial derivative of f with respect to x, and that gives us 0. So we put 0 plus, we look at this, 3h squared k, and will give us 3x squared y, and then we look for the partial derivative. Now look at cross partial. Going to the cross partial, see we have 2. Cross partial there is 2, so we have 2 plus. Then we have 3 again, 3xy squared. Now here we have 0 plus y cube, and then we also have 0. Okay. Now here we can now collect them one after the other. We have minus 10 minus 4x plus 4y. Now here is minus. You see, here is minus 2x squared. You know this is 2 factorial, and so 2 factorial is 2. So if you times it here with this 4 can divide this 2. We have this. Now, if we go this way, we'll have plus 2xy. You know how? Because this 2 factorial can cancel this 2. 2 factorial is 2. So it cancels here, we have 2xy. Then if we go here, it becomes 0. Then plus. If you go here, because of this 0, so it becomes 0. Now, look at this. 2 times 3 is 6. And then 3 factorial is 6. So what it means is that we have x squared y. Right. Now if we go here, is 0. This place is 0. Okay. So what we have there is this. So it means that f of x minus 1, x plus 1. If I like, I'll say f plus 1, and then y minus 2, because y was minus 2, y plus minus 2 give me this. So x plus 1, y minus 2 is equal, f of x plus k now become, f of x is this. So it now become minus 10 minus 4x plus 4y minus 2x squared plus 2xy plus x squared y. So that is the expansion of this function. That is the expansion of this function. It is very simple. If you know binomial expansion very well, and so we can now apply it with Taylor series. You can expand the series. Very simple. So what you need to do is to have a playback and then look at it properly so that you know it, because it's very essential in your study. It's very essential when you'll be doing the application of all these things. In case you want to write this back in its powers that we're given, we can write that x squared y plus 3y minus 2 equals minus 10 minus 4. Then you write this x plus 1. You know, we are expanding about x is equal 1. So x minus, okay, say x minus 1. Sorry, x minus 1. That is what we are expanding about. X minus 1. X minus 1. And then for here we have plus 4 y plus 2 minus 2 x minus 1 squared plus, this is where we are expanding, so we have 2x minus 1 squared y plus 2 plus x minus 1 squared, then y plus 2. So this is another way that we can express this. So another way. So that is how it works. Now we are going to look at maximum and minimum value of functions of two variables. Maximum and minimum. Minimum of functions. All right. Now let z equal f of xy here be a function of two variables x and y. Z is said to have maximum or minimum. To be maximum, all right, to be maximum or minimum at point AB if 1 partial z partial x equal partial z partial y, which is equal 0. Then number 2 condition is that partial square z partial x square times partial square z partial y square minus partial square z partial x partial y square greater than 0. Now see, if this number 2 is greater than 0, it means there is maximum or minimum. So we then test for maximum. For maximum. Now 1, if partial z partial x equal partial z partial y, which is equal 0, number 2, and partial square z partial x square times partial square z partial y square minus partial square z partial x partial y square is greater than 0, and partial square z partial x square partial square z partial y square are both are both negative at AB, then Z equal F of SY is maximum. It's maximum. All right. We also look at minimum. Now, if partial Z partial X equal partial Z partial Y, which is equal 0 at a point AB, and again partial square Z partial X square times partial square Z partial Y square minus partial square Z partial X partial Y square is greater than 0, and partial square Z partial X square partial square Z partial Y square are both positive. That is, both have positive value, positive at AB. Then Z F of SY is minimum. You know, here they have, yes, they have positive there, so they have, here is minimum. It will be minimum at that point. All right, so to apply this condition, we want to take one example and demonstrate how we can find the maximum and minimum point of function of two variables. Okay, so let's look at this example. Determine the maximum and minimum of the function Z equal x cubed plus y squared minus 63 times x plus y plus 12xy. Right, so the solution is in this form. I have that Z equal x cubed plus y squared minus 63x plus y plus 12xy. Now, partial Z partial x, look at that, partial Z partial x will give me 3x squared minus 63 plus 12y. All right, partial Z partial y will give me, okay, this is x cubed, is x cubed, A2 is x cubed, so we have 3y squared minus 63, yes, plus 12x. So at stationary points, partial Z partial x will be equal partial Z partial y, which is 0. So that means this equation become, if here is 0, this equation become 3x squared minus 63 plus 12y, and then this one also become 3y squared minus 63 plus 12x. Okay, equals 0. So this gives us 1. This is 2. Okay, now if we divide this, divide it through, we can divide this by 3. Yes, we also divide this. We will have something like this: x squared plus 4y minus 21 equals 0. This one will give us y squared plus 4x minus 21 equals 0. All right, so let me call this equation 3. and call this 4. Now, subtracting 4 from 3. If I subtract equation 4 from 3, I will have something like this: x squared minus y squared. Then we'll have minus 4x minus y. You know why? Because this time this will give me back this 4 plus 4 y, and this is giving me minus. You know, I'm minusing this way, so it will be equal 0, which I can also write it as x minus y, then x plus y minus 4 equals 0. If you multiply these two, you'll get back everything here. So that is what it means, which implies again that x minus y equals 0, or x plus y minus 4 equals 0. We'll take note of here because we'll be using that place. So now from here, now we see that from here x minus y equals 0 implies that x equal y. So I can now substitute x equal y into 3. X equal y into this 3. So we then have x squared plus 4x minus 21 equals 0. See that? So this is a quadratic, which 7 minus 3 give me 4 by factorization. Then 7 times minus 3 give me minus 21. So that gives me that x plus 7, x minus 3 equals 0. Meaning that x equal minus 7 or x equal 3. These are points. X equal minus 7, x equal 3. So when x equal minus 7, so if you put here x equal minus 7, so it also implies that y equal minus 7. Now when x equal 3, so also implies that y equal 3. So then I have a stationary point of this form, minus 7, minus 7. Another point is 3, 3. So I have those points. All right. Then I can come here again. Here I see that from here x plus y equal minus 4. You know, we were using 1. Remember 1. So it means that y equal, yes, if I take this to here or here, I will have that 4 minus x. Y equal 4 minus x. That's what it means. Taking here 4 minus x. And now I'm going to substitute into 3. That's the one I will use. So we have x squared plus 4. 4 minus x minus 21 equals 0. This gives me x squared plus 16. 4x minus 21 equals 0. So x squared minus 4x minus 5 will be equal 0. Now look at this one. This is quadratic again, which tells me that this is minus 5 plus 1 and give me minus 4. And then minus 5 times 1 give me minus 5. So the factors are plus 1 equals 0. And that means x equal 5 or x equal minus 1. So when x equal 5, if you substitute it here, when x equal 5, you will see that you have something like this: x plus y minus 4 will imply 5 plus y minus 4 equals 0. So what is that? It means that y equal minus 1. So when x equal 5, y is minus 1. We have a point there. X is 5, y is minus 1. So again, when x equal minus 1, if I put it here, I will have minus 1 plus 5 minus 4 equals 0. That implies that y equal 5. So I have another point. When x is minus 1, y is 5. So we have about 4 points. Now we want to find the maximum now and the minimum. So before we do that, we take partial square z over partial x square. Partial square z over partial x square is the differentiation of this with respect to x. So that will give you 6x. Then partial square z partial y square. Look at there. Partial square, partial square, partial z partial y. So partial square z partial y square. You see that? It's only here we find y. So we'll give us 6y. 6y. All right. So we want to test the first points. These first points. Let's test this place. Testing minus 7, these points. Let's see whether this point is maximum or minimum. We know that partial square, partial z, partial x equal partial z, partial y equals 0. That is the first condition, because if you put it there, you have 0. All right. Then partial square z. Now look at this. Partial square z, partial x square times partial square z, partial y square minus partial, okay, we will need here partial square z, partial x, partial y. That is, go to x, differentiate with respect to y. Look at there. If you go to x, differentiate with respect to y, we'll have 12 only there. So meaning that partial square z over partial x partial y square, will it be greater than 0? This is the condition. So let us see. This one, we have seen it that it is 6x, and x here is minus 7 times, we have another one, 6y. So that will give us 6 times 7, no, 6 times minus 7, minus 7. 6 times minus 7, minus 12 square. Okay, so we want to see whether it's greater than 0. And then, if it is greater than 0, then we will now decide whether it is maximum or minimum. Okay, let us do this. 6 times minus 7 give us minus 42. So this is also minus 42. If you times the 2, 42 times 42, give us 1764. Now this is 144. So 1764 minus 144 will give us 1620, and it is greater than 0, is positive. So since this one is positive, the point that we are using is minus minus, that is negative negative. It means that z equal f of xy is maximum at these points, at minus 7 and minus 7. So I'd like you to carry out the other test for the other 3 points. See, this one is 3, 3. What you do now is you just carry it 3 and 3. Put 6 and put 3 in the place of x, times 6 again, put 3 in the place of y. Then 6 times 3 will be 18. 6 times 3, 18. Then you say 18 times 18. Give you a value. Then put 12 square. Minus 18 times 18 from 144 and see whether it's greater than 0. If it is greater than 0, then that point 3, 3 will be minimum. How? Because it is positive, positive. So the same thing will happen to these points. Of course, these points, one is negative. So, but if you put it here and also evaluate it, if it is less than 0, then it is a saddle point. It's not maximum or minimum. It's a saddle point, provided here is less than 0. It's a saddle point. But if here is greater than 0, it means there is maximum or minimum. Then for you to determine the one that is maximum, you look at this point, the point that you are testing. Whether it is negative, negative, you know it's maximum. If it is positive, positive, you know it's minimum. So that is how it works. I'd like you to do that as an exercise. Thank you. Let's look at another application. Now we will look at another application, which is the Lagrange method of undetermined multiplier. So let's g of sy be function of two variable x and y. Let f of x, y equals 0 be a curve. Now, for g of xy, or to find the maximum or minimum of g of xy, for g of, to find, let's do like that, to find the maximum or minimum value of g of xy on the curve f of xy equals 0. We define a new function, and this function say h of x, y, lambda, which will be equal g of xy plus lambda f of xy, like that, subject to the condition that partial h, partial x equals 0, partial h, partial y equals 0. Now, you see the parameter lambda independent of x and y. And it is called Lagrange multiplier. Okay, so if we want to use the Lagrange method of undetermined multiplier, when we are given a function, because we'll be given a function, we'll also be given a curve. Now, for this function to have maximum or minimum on that curve, so for us to get the value, what we will do is to define a new function, this one, and we say g of xy plus lambda f of xy. And then when we do that, we do it subject to this condition that partial f, partial x will be 0, and then partial h, partial y will be 0. The parameter lambda is independent of x and y, and that is what we call the Lagrange multiplier. Now we'll look at example. Let's pick example so that we see how it works. Okay, so let's look at this example. Find the maximum or minimum point of the function g of xy is equal to x squared plus y squared on the curve f of xy is equal to y plus x squared minus 1. Now, we have the solution that we have that g of xy is equal x squared plus y squared. Now f of xy is y plus x squared minus 1. So if we define a new function xy, f of xy and lambda, then we will have f of x squared plus y squared plus, we say we define a new function when we have g of xy plus f of xy. So we have like this. Lambda, now we have y plus x squared minus 1. So we have added it. Now, partial h, partial x is 2x. Then we have plus 2 lambda x. If I use lambda to times it, I will have lambda x. So when I differentiate it, I have 2 lambda x. Now I also have that partial h partial y will be equal to 2y plus lambda. Yes, that is what it will mean. Because if you have 2y, then go here, you have lambda. Okay. Now the condition was that we is subject to this condition that partial h partial x equals 0, partial h partial y equals 0. So what we do now is to have that 2x plus 2 lambda x equals 0. That is equation 1. Then we have again that 2y plus lambda equals 0 is equation 2. Which means now we have 2 there. But there is another one that h of lambda is y plus x squared minus 1. Let's define up to 3. Now this is the curve that is given. Now for this one, can write that 2x 1 plus lambda equals 0. I just factor out 2x, which implies that x equals 0 and then lambda equals minus 1. That is what this means. Now if I put x equals 0 in 3, yes, because that is where you have x. So if I put it there, I will have that y, look at x equals 0. So y is equal 1. Now if I also put lambda equal minus 1 in 2, that is where I have lambda is 2. So we have 2y minus 1 equals 0, which also implies that y is equal 1 over 2. So I also have that y is equal 1 over 2. Now, if I put y is equal 1 over 2, if I put y is equal 1 over 2 in 3, so putting y is equal 1 over 2 in 3, so that I can get the corresponding value of x. I now have 1 over 2 plus x squared minus 1 equals 0, which means 1 over 2 minus 1 plus x squared. Now, what would this give? Equals 0. 1 over 2 minus 1 is minus 1 over 2 plus x squared equals 0. And that implies that x squared is equal, this will come here, 1 over 2. So x is equal plus or minus square root of 1 over 2, which is plus or minus 1 over 2. So it means that what we have for y is equal to 1 over 2 is that, this thing is 2 plus or minus now, plus of this square. So we have the points. The points now become y. No, the first one is plus or minus. So we have point like this: 1 over 2. Then y is 1 over 2. We have another point minus 1 over 2, and then y is 1 over 2. We have the point. So these are the points now. You will be able to locate the point. Now what we need is we find the maximum or the minimum points. Now let's test for this. Also test for this, and then we find maximum. But we also have, now see another point. Y is 1, x is 0. It's another point. Yes, so we can now put that one also. Y is 1, x is 0. These are the 3 points. So let's test these 3 points and see. G of xy equals x squared plus y squared. So let's go with this. That means g of 1 over root 2 and 1 over 2 will be 1 over root 2 squared plus 1 over 2 squared. Of course, that will give me 1 over 2. And then you give me 1, okay, plus 1 over 4, which is the same as 4 times 2 plus 1, which is 3 over 4. Now if we go for these points, at that point we have g of minus 1 over 2 and 1 over 2. It will be minus 1 over 2 squared for x plus 1 over 2 squared for y, and that will give us the same 1 over 2 plus 1 over 2. If we use this and time this, we get 2. So and this time this is say 1. Now this resembles this, so you can go straight to say 4 over 2. 3 over 4. Now for another point, which is the other one, we have 0 and 1. 0 and 1. So at that point, we put 0 squared plus 1 squared, which is equal 1. Okay, now this is 1. This is 3 over 4. This 3 over 4. Which one is maximum? We see that at 0 and 1, g of x, y is maximum. You see the method of this one. I look different from what we were doing in the other pattern of maximum and minimum. So now g of xy is here, is maximum here, because 1 is greater than 3 over 4. Okay, therefore at 1 over root 2, 1 over 2, and minus 1 over root 2, 1 over 2, g of xy is minimum. Minimum. It's minimum at those points. So this is how we can use the Lagrange multiplier to determine the maximum and the minimum value of a function on any given curve. Now the next application we want to look at is normal and directional derivative. Let phi x y z equals c be family of surfaces then the phi will be equal the phi times the r. Now if the phi times the r equals 0, equals 0, the phi and the r are perpendicular to each other. They are perpendicular to each other. Now, you see, the phi is the normal vector to the curve, here, to the surface, to the surface is phi x y z. Now, it is assumed that the students have taken some courses on the tensor and vector analysis. So you will know about grade 5, you know about what we call curl of a function. And so that we just assume that, I assume you have taken a course on that. Now, I'll only talk about, we say if this is differential operator there. So del phi times the r equals 0. If it is equals, it means they are perpendicular. You know, they will form an angle 90 degrees, and you know that for two vectors to form angle 90 degrees, it means they are perpendicular. Now, we also see, like this for normal. We are talking about normal now, please. We are talking about normal. We are trying to define normal first before we now go to directional derivative. So we're talking about normal. So if they are perpendicular, it means they form angle 90. And you know how, you know the angle between two vectors that are perpendicular. Now angle 90. And cos 90 will give you 0. So if the phi times the r is 0, it means that they are perpendicular to each other. And what it means is that the phi is the normal vector to the surface, normal. Okay. So now we'll pick example and see how we can apply this. Now the example is, find the unit normal vector to the surface z square is equal x square plus y square at the points x is equal 1, y is equal 0, and x equal minus 1. Okay, so we have said that del phi is the normal vector to the surface, is one that is not coming normal to the surface. So we should know that, and we can use that. It is normal vector to the surface, this surface here. Okay, surface equals C. Now see, because of this information, we can take the solution in this way. Let phi, we'll define phi now, and this is what they are giving. So phi will be equal x squared plus y squared minus z squared. I just also mean is that there, I need the differential operator. Now there is defined as, we define there as I partial x plus j partial y plus k partial z. It is believed that you have done classical mechanics, you done the course of classical mechanics or vector and tensor analysis. You know what I talk about there here. So it means that if I do this, so what it means is that there phi, which is the normal vector we are talking about, is the same as partial x plus j partial y plus k partial z times phi, and phi is x squared plus y squared minus z squared. So then 5 will be that. Now, if we multiply this, we will have I partial x of x squared plus y squared minus z squared. We times that plus, we times this, we have j partial y of x squared plus y squared minus z squared. Now if we times with this again, we have plus k partial z of x squared plus y squared minus z squared. So now this is the same thing as I. If I differentiate it with respect to x, I will have 2x plus j. Differentiate it with respect to y, I will have 2y plus k. If I differentiate it with respect to z, I will have minus what? 2z. Yes. Then at the point 1, 0, minus 1, that is what they are giving. Then we have, if we put 1 here, we have I2 times 1 plus J2 times 0 plus K. Okay, here will be minus, let's just say minus 2Z, and Z here is minus 1. Okay, so what we have is 2I, this will go, plus what? 2K. So that is the 5 equal this at the point 1 for y, x, 0 for y, and minus 1 for z. Now, what we need is unit normal. And look at that. The question, find the unit normal vector. We know of normal vector, which is the 5. So we want to find the unit normal. You know that I can write it to be 2I plus k. So let me simplify it there. So as we are looking at unit normal. Now how do we define unit normal? See unit normal. We define unit normal vector. Then 5 over the magnitude of the 5. You know the magnitude here, that is the modulus. And that will give us that unit normal become the unit normal vector. Now become what? Del phi. We have already known del phi to be this. So we have 2I plus 2k. Let me put it that way. Divided by the magnitude of del phi. Now the magnitude is given by what? 2 square plus 2 square. Of course, we know this of our vector, elementary studies of vector. When we talk about magnitude or modulus of a vector, we take the modulus this way. And that will give us 2I plus 2k over root 8. Over root 8. So which is the same as 2I plus k. Now root 8 is the same as root 4 times root 2. I can write it like that so that I need to cancel these two. So which is the same as I plus k over root 2. Look at that, because this is 2. So 2 cancel 2, so I have I plus k over root 2. Right. Like I can rationalize it. I can rationalize it to have root 2 over root 2, which is the same as root 2 I plus k over what? Over 2. Yes, so that is how we get the units normal, and we also get the normal vector. The normal vector. And you see that it is because of partial derivatives that we can do all this. So that is the issue there, the application. Now we'll also look at directional derivative when we talk about directional derivative. Next one is directional derivative. And now the components of the phi in the direction of a vector v is called the directional derivative of phi in the direction of v. V is the vector. We have just finished the phi, so the components of the phi in the direction of vector d, we will express a vector. So the component of that the phi will be the vector d is called the directional derivative of phi in the direction of d. Now, to understand it properly, we'll pick example, and then when we find the phi, we see how we use another vector d to multiply the phi, so that we now get the directional derivative. Let's pick. So now we are going to find the directional derivative of phi of xyz is equal x squared y squared plus yz cubed at the point x equal 1, y is equal minus 1, and z is equal 1. In the direction of this vector, this is a vector, and this is the vector d that I'm making reference to here. So now, another thing I should put so that we understand it is that we are saying that directional derivative of phi in the direction of d, written, let me put that, written as, see how we write it, the phi times d. So what we'll do is, d is a vector. We'll find the phi, then we multiply it by d. So in the solution, we have the I partial x plus j partial y plus k partial z times phi, and then phi here we have x squared y squared plus y z cubed. That's our phi as given. Now, if we differentiate this with respect to x, because that is what here means. So we have I 2x y squared plus j. Differentiate this with respect to y. You have 2x squared y plus z cubed. That's if we differentiate it. What we are doing, just use this to multiply first, but I assume you, from what we have just done, So multiplying it with this and differentiating it with respect to y will give us this. Now, if we go for here, we have plus k, now we are differentiating with respect to z, and then we will have 3yz squared at 1, the point that they gave us is 1 minus 1 and 1. So 1 minus 1 and 1, at this point you will have that the differential operator there times phi will be equal to I2, then 1, this is y, this is minus 1 squared plus, squared plus j, we have 2, 1, and then minus 1 plus plus 1, and then 1 cube plus k, and then we have 3, y is minus 1, and then we have 1 cube. We just fix this point for x, y, and z. So if you do that, we'll have minus 2i here. Because not minus, because here is square, so become plus. Yes, plus 1. So 2 times 1 is still 1. Now here is minus 2j. Yeah, minus 2j. Minus 2. Okay, we have here minus 2 plus. Look at that. Minus 2 plus 1. minus 2 plus 1 will give us minus 2 plus 1 will give us minus 1, so minus j. Then here will give us minus 3p. So that is what we have. That is the 5. Now we know that vector d was given to be 3i plus j minus k. And we say that for us to get the directional derivative, that is the 5 times d times vector d, we have 2i minus j minus 3k times 3i plus j minus k divided by the magnitude of d. So which is, we have, this will be 9 plus 1 plus 1, because you know what we have, 3 squared, 1 squared.